Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and this lecture is going to build off our last lecture on adiabatic processes. Now, adiabatic just means that basically no heat exchange is happening outside of the boundaries of this parcel that we're talking about, or parcel of air. Uh, so this lecture is going to focus on rising air and what forces air to rise. Now, there's a number of different mechanisms at play here that get air to go from one level, one altitude to another and back down again. So we're going to talk about those. That's what this lecture is going to focus on. So first off, just a quick recap. This is kind of how I ended the last video. Adiabatic lapse rates. As parcels of air rise, they cool at a given lapse rate. Rate of temperature change with height, degrees Celsius per meter, is typically what we use. The dry adiabatic lapse rate is when an unsaturated parcel of air cools at a rate of 1 degree Celsius for every 100 meters. Unsaturated meaning that relative humidity is below 100%. Dew point lapse rate is also changing at a rate of 0.2 degrees Celsius for every 100 meters when that air parcel is unsaturated. That's the important distinction here, is when it's unsaturated, you are trying to calculate the increase or decrease in temperature within an air parcel using the dry adiabatic lapse rate and the dew point lapse rate. The moist adiabatic lapse rate or saturated adiabatic lapse rate, SALR or MALR, depending, you'll see them both, is when a saturated parcel of air is cooling at a rate that varies from between 0.4 degrees and 0.9 degrees Celsius. So as it's rising, it is cooling at that rate. The lifting condensation level is our last one. I don't have that on here, but that's just the level where you go from an unsaturated parcel of air to a saturated parcel of air. That's just the base of your cloud banks, for example. So adiabatic processes deal with the changing temperature of a parcel of air due to it rising or sinking adiabatically or lacking heat exchange outside of the boundaries of this parcel, right? Basically, we're dealing with parcels of air that are rising and cooling, but what drives that rise? Well, a number of different methods or mechanisms. The first one, if you've taken 104, this one should be intimately familiar. Orographic lifting. Orographic lifting is the process in which mountains or highlands act as barriers to the flow of air and force that air to ascend and rise up in the altitude. The air cools adiabatically, clouds and precipitation may result. So here in our little example, we see airflow being pushed up over a mountain. And as it's pushed up, that air is being forced up, it is cooling at that dry adiabatic lapse rate until you get to a level where your air temperature and your dew point are equal. And then this point here is our LCL. We remember that from the last video, our lifting condensation level. Now, what does this look like in the wild? Well, here we are in coastal California. This is from the famous Highway 1. And we see as air is coming in off the coast and being pushed up by these headland mountains, you've got this cloud base right here. Right? So as air is coming up, it's hitting this boundary and being pushed up. As it's being pushed up, it's cooling at that dry adiabatic lapse rate, or DALR, and DPLR, the dew point lapse rate, right? Once it rises above here, above this point right here, it is cooling at the saturated or moist adiabatic lapse rate. Whoops. My bad. Lapse rate. Here, this point is just our lifting condensation level. Excuse the sketching. I'm using a mouse, and it's not always easy to draw on. So we can see that here. So, oh, even had a nice little graphic that I forgot about. So this is our windward side here. So this is the windward side of this headland system. Now, that would be akin to something like this, right? So what happens here is a few different things. One, you've got this rising parcel of air that's being forced up and over a mountain. Now, as it rises, it cools. As it cools, it condenses. As it condenses, it precipitates out, right? It's raining out. Now, once you get to the crest of this mountain, for example, right here, air is moving up over the crest, maybe a little bit lag here, and then it starts to fall again, as we see here. Now, if we were to look at this example, once we hit that point, the lifting condensation level right here, our temperature and dew point are both equal to 10 degrees Celsius. Then we're changing at our saturated adiabatic lapse rate of 0.6 degrees Celsius for every 100 meters. Right? Easy peasy. Just kind of reinforcing those things that we talked about last time. Now, if you were in Geography 104, this would be your moisture in the atmosphere, or lovingly named Mount Doom, where you're looking at a parcel of air traveling up and over actually a stretch from Eureka to Red Bluff, California. So, continue on here. This is what that looks like in a neat GIF format. Air is rolling up over this mountain, falling out, but the fact that it's being pushed up is what's causing this cloud formation to occur. We're looking at the leeward side of this system, or downwind side, so past the crest. Same thing that you see happening here or here. So it's that rising of the air through just the topography alone, the forcing of that air up, that's causing it to decrease in temperature. And we'll talk about, there are names for these clouds. We'll talk about those in a few lectures. For now, just focus on the fact that this is the process that's occurring. The next big one, frontal lifting. Now, when we say frontal lifting, we're thinking of warm fronts or cold fronts. We've heard talk of warm fronts and cold fronts most of our lives, I assume. Basically, looking at a warm front is a front of warmer air moving across the land. Cold front is the same thing for cold air, right? So here, if we had a cold air front or a cold front moving through, we'd have colder air pushing warmer or towards warmer air. The wedge kind of shape here, or this kind of blunt nose shape, is going to force into the air. Now, warm air is less dense. Cold air is denser. So that's going to cause the warmer air to rise. This is typically what we see this symbol referred to, is this blue line with triangles jutting off it. That's typically what we see for a cold front. As opposed to this one, where you've got this wedge of cold air here. Warm air is moving in, forcing itself up over the front, or the parcel of air here. You got your warmer, less dense air, and your colder, denser air. That wedge that is being pushed along by this air parcel behind it is what we call a warm front. Now, both of them relate to air being moved or vertically by whatever frontal system is occurring. Now, if we look here in the warm front, we typically see this as a red line with semicircles dotting along it. So those are typically what we'll see. We'll talk about how to interpret weather maps and what those symbols mean later on. Maybe in the next lecture or a couple lectures down the road, but we'll get there for interpreting what those mean. So here, just a little bit more in-depth diagrams. You just kind of look at warm fronts and cold fronts. So here, the frontal zone slopes up and over the colder air mass ahead of it. Warm air rides along the front, up and over the cold air mass, cooling as it rises, producing clouds and precipitation in advance of the surface warm front. Now, clouds are because we're rising, we're hitting that saturation point, and we're condensing. We're getting cloud formation, and then precipitation as a result. Because the lifting is very gradual and steady, generally widespread and light intensity precipitation develops ahead of a warm front. A nice drizzle, for example. Initially, a warm air mass, which we see in kind of the yellowy orange colors, nudges against a colder air mass, which we see in those kind of gradational blues, ahead of it. So we're seeing that this is just separated by the warm front. That's that box that we're seeing where the arrows are moving up. They're bounded by that box. The lighter warm air behind the front is lifted upwards and overrides that colder air. Now, as we said, a layer of thin clouds is occasionally observed more than 1,000 kilometers ahead of a surface warm front. As the front gets closer, these clouds start to thicken. We see that happening in the GIF right now. And eventually that light precipitation will start to fall. Because the frontal surface gently slopes up and over the cold air mass ahead of it, the upward motions associated with warm fronts are not as strong and vigorous as they are in a cold front. That's an important distinction, and we'll talk about that when we kind of look into how storm systems develop, because warm fronts and cold fronts produce wildly different meteorological phenomena. Speaking of which, here we have our cold front. So initially, the cold air mass wedges into the warm air mass ahead of it, separated from each other by the cold front. The lighter warm air is lifted up by the denser colder air. And if enough water vapor condenses, our clouds start to develop. If condensation of water vapor persists, precipitation may develop, typically in a narrow band just at the leading edge of the cold front, so just ahead of it. Due to how steep that slope is, vigorous rising motion is often produced, leading to the development of showers and occasionally very strong thunderstorms. And that's kind of the distinction here. So with a warm front, you might get this nice drizzle. With a cold front, you could get some pretty severe thunderstorms. These bands are pretty narrow. They're the ones that are come out of nowhere and are gone before you know it kind of storms, if you know what I'm talking about. We can look, for example, at this map here. So this is kind of moisture and cloud cover across the central portion of the United States. We can see Wisconsin and Minnesota and all of our local states here. So if we were to look right here, this is a cold front moving through. Notice that narrow band of clouds surrounding where we have that blue line drawn in, right? So we have this narrow band of clouds that go here and here, right? So between those two lines, that's where our cloud band is. If you look up here, this big broad cloud bank here, that's a warm front pushing in. And we can see in this example a much more extensive cloud cover, potentially some light precipitation going on therein. Pardon me. The next one is a phenomenon we call horizontal convergence. Now, we haven't necessarily gotten into all the nuances of atmospheric circulation patterns yet, and we're going to dive into that very soon. But horizontal convergence is basically when you have a low pressure system at the surface that leads to converging air. Now, if we think of it, when we talk about a low or a high pressure system, we're talking about either a buildup of pressure or a lack of pressure in regards to the areas around it. So with a low pressure system, air is rushing in to fill that low pressure void, whereas a high pressure system, it's rushing out to, equilibrate to the air around it. So what you have is convergence at the surface, divergence aloft, and that's what we're seeing right here. Now, these low pressure systems can form some pretty famous types of storms, one of them being tropical cyclones or hurricanes or mid-latitude cyclones as well. So you've got that low pressure system right here, for example, and air is rushing in to fill that deep, deep low pressure system. So that can also lead to, as that air is rushing in and rising up, it's decreasing in temperature. As it decreases in temperature, you're forming clouds. Then another phenomenon called localized or free convection. Now, what's going on here is as it suggests, a much more local basis. Now, you could have the sun coming in, incoming solar radiation hitting this pond, for example. Now, as it hits that pond and it's being heated by the sun, you are having rising thermal energy coming up, energy evaporating or water evaporating off the surface. As it rises, it condenses. You can see here's our lifting condensation level. Now, what does this look like? This is a little bit different. So this is much more, kind of this happens where you have a lot of water, for example, places like Minnesota, Wisconsin, Florida, where you've got a surplus of surface water is where this type of phenomena will occur. So it might look like this. Notice all these little discrete clouds formed from kind of local processes. These are cumulus clouds. And we'll talk about what cumulus clouds are in a future video, but we can see them here at the surface or just above where the cloud bank is. We can see them here. These are also spots of localized or free convection, where you've got all these clouds popping up out of nowhere because of the heating of water on the surface. So what causes air to rise? Orographic lifting, frontal lifting, horizontal convergence, or localized free convection. Now, these four phenomena are often acting in combination. Now, if we consider the term atmospheric stability, that's the condition of the atmosphere that determines whether air is going to rise spontaneously or not. And that's where we're going to pick up and talk about in the next video. So we've learned what forces air up. We've learned how air responds to being forced up. Now we're going to look at some of the environmental stimuli around it that determine whether or not that air parcel is going to rise. So we'll learn what drives that rise, but now we're going to learn whether or not it will rise. So hope that made sense. I will see you in the next video. I hope you have a great day. And we've got, I think, one more video in this run of kind of humidity and moisture. And then the next week we'll be moving into, or the next group of lectures will be moving into some other topics. So sit back, we got one more to go, and we will see you in the next video. Thanks.